Hello and welcome. We are going to talk about confidence intervals today, specifically a confidence interval dealing with proportions, so categorical data. We're estimating a population proportion. So today's objectives to identify appropriate inference methods for confidence intervals and construct a confidence interval provided conditions are met. So let's get started. Um, by the way, that word inference is the part of the year that we are heading into. It's pretty much going to take up the rest of the year. The word inference basically means we are taking something that's true for a sample and using that to infer or estimate what's true about a population. So we're going to start with something called a point estimate. And these beginning couple of slides is something that I talked about in class, but I feel like it's good to recap on. So a point estimate is basically a single statistic that is based on a sample data. So it's our statistic from a sample that is used to estimate a population parameter. So in this case, we're going to talk about a proportion because we're dealing with categorical data for today. So, for example, Gallup poll reported that 32% of parents have participated in surveys in their child's school. So, that 32% is a point estimate that's estimating or trying to infer the true proportion of parents in the US who participate in school surveys. Um, Point estimates are a very simple approach to estimating what's true about the population. But downside is that it's not always going to be very precise because we know that even with random samples, those statistics are not always going to be spot on. They could be a little off, they could be a lot off just by randomness, just by the fact that random isn't going to necessarily always be perfect. So we have to realize that. So again, a way to think of that is if I took another sample, will I absolutely get the same 32%? Probably not. So, confidence intervals are a way of estimating what's true about the population with more confidence because we are adding in what we call a margin of error. So, it's also used to estimate the unknown population parameter that we're looking for, but it uses a margin of error to create an interval. So, our basic formula for a confidence interval is we take our statistic, so that's the number that we got from our sample, and then we add and subtract to what we call a margin of error. So, for example, with our survey about do parents answer school surveys, we got 32% from the sample that we took, and then our margin of error turned out to be about 3%. And we'll get into later in a couple slides on where that margin of error comes from. But 32% plus or minus. So I always think of the margin of error as like the give or take. So it's 32%, give or take 3%. So we're pretty confident, we're pretty sure that the true proportion of all US parents who participate in school surveys is somewhere between 29 and 35%. And I can feel more confident in that interval than I could in just that one single point estimate. So we're going to go ahead and this is what we did in class, constructed our very first confidence interval to estimate the true proportion of coin flips that land on heads. And we pretended for a second that we don't know what that true proportion is or should be. So we went to random.org and flipped a coin 50 times, made sure to select a coin with a clear heads or tails, and then found our sample proportion for the coin flips proportion of coin flips that landed on heads. For this example, so this is your point estimate. Remember, that's your one single number based on a sample that we're trying to use to represent what's true about the population. So to create our interval, this is on our formula chart. It tells us to do a confidence interval. We take our statistic and then we add and subtract. These two things multiplied are the margin of error. So we do a critical value times a standard deviation of the statistic. So our statistic in this case would be our sample proportion. Critical value, we use the letter Z star to represent that. We'll come back to this and talk more about it in a few slides. And then our standard deviation formula for proportions is square root of p times 1 minus p over n. And for now, we're going to use 1.96 for our Z star, and we'll come back to what that means later. So for example, suppose when I went to random.org and flipped some coins, I got 28 flips out of 50 flips, or 28 heads out of 50 flips. So 28 out of 50 is 0.56. So I'm going to use that to plug into this formula and to get a confidence interval. So plugging that in, 0.56 would be the p hat, that's my sample proportion, plus minus, I'm going to leave the 1.96 as Z star, and then square root of p, so we're using p hat as an estimate for p, so 0.56 times 1 minus p, which is 0.44, divided by n, which is the number of times I flipped the coin, which is 50. Okay, doing a little math, I like to do the square root part first. So I did that and got, so square root of 0.56 times 0.44 over 50 is 0.0702. Multiplied that by 1.96 and got 0.1376. And then once I did that, I added and subtracted. So 0.56 plus 0.1376, and I got and then 0.56 minus 0.1376. So when I did the minus, I got 0.422. When I did the plus, I got 0.698. So this is now my confidence interval for the true proportion of coin flips that land on heads based on my sample. So the way that I interpret this interval, and this is always something that you should do. We are always interpreting these numbers from this point forward. The way to interpret the confidence interval is something like this. So I would say I am blank percent confident that the true proportion of whatever thing that I'm estimating is between these two numbers. So for this example, I'm going to say that I'm 95% confident. The percent confident comes from what we used for Z star. So that's something I will talk about in a couple of minutes, but just know that that Z star equals 1.96. If I'm using that as my critical value, that gives me a 95% confidence interval. So I'm 95% confident that the true proportion of coin flips that land on heads is between 0.422 and 0.698. Okay. In other words, I'm pretty sure, 95% sure, that somewhere between about 42% and 70% of coins will land on heads. Somewhere in there. That's what I'm sure of. Right? The confidence level, again, that percentage depends on what we use for Z star. So for a Z star of 1.96, we are 95% confident. Another thing that you might be asked to do is interpret a confidence level. Now, this is not something that we always need to interpret, right? So we're always interpreting the interval, because if you calculate the interval, you want to tell what that interval means. The confidence level, which is the 95% part, it's the success rate of the method that you're using, is something we only really need to do if we're asked specifically about it. And what that confidence level refers to is if I were to take many random samples of this size from this population, doing it the same way that I did it the first time, about blank percent, whatever is your confidence level, about that percent of the intervals you create should contain the true proportion. Okay, so for example, if I was interpreting the confidence level for my problem about the coin flips that I just did, I would say for many trials of 50 coin flips, or if I were to flip a coin 50 times and I do that repeated times, many times in a row, about 95% of all intervals that I calculate from each of those samples should contain the true proportion of coin flips that land on heads. In other words, if I were to use that same method over and over again to calculate a whole bunch of confidence intervals, I can expect that the correct proportion should be included in that interval about 95% of the time. And I demonstrated this with, when we did this in class, I had everyone put their confidence intervals on a graph. And what we saw, or what we hopefully saw, was that when we looked at everyone's, most people's confidence intervals for the coin flips included 0.5, but not all of them. And so what we kind of saw there was that using that method, using that sampling method and calculating intervals, most of the time, about 95% of the time, we got the correct answer, but sometimes we didn't. So that's what that confidence level is referring to. So let's talk a little bit more about that Z star. So we've successfully constructed a 95% confidence interval. So if we were to construct another interval, but instead of using 1.96, I now used a different number. I'm going to use 2.576. So I want you to think about how that might affect our interval. This new interval will have 99% confidence. And if you think about just the math part of it, right? Z star, that's the critical value, is multiplied by the standard deviation of the statistic, and that gives you my margin of error. So if we're using a bigger number for Z star, it's going to give me a bigger margin of error, which is going to make my interval wider because I'm subtracting and adding a bigger number. So using a larger value for Z star should give us a wider interval, and that new interval will have more confidence. It'll have 99% confidence, right? So way I want to describe this. So imagine that I asked you to rate your confidence, is what that says. Rate your confidence from 0 to 100. So how confident would you be if I asked you to guess my age within 10 years? So if I just said, hey, guess my age within 10 years. If you're right, you get a prize. How confident would you be that you could get the correct answer within 10 years? So if you're 10 years off in either direction, you still win the prize. You're probably going to be fairly confident, hopefully, right? But then if I ask you to guess my age within 5 years, right? So now my margin of error has decreased. To win a prize, you have to get closer to my actual age. You're probably a little less confident. And then if I asked you to guess my age within 1 year, I've made the margin of error even smaller. In order for you to win a prize, you have to get it within that small margin of error. Right? You're probably even less confident. And then if I said it's within 6 months, within 3 months, within 1 month. So the smaller my interval gets, the less confident you are that you're able to estimate within that margin of error. Right? So as the interval got smaller, your confidence probably got smaller. So I can go through the same example. How confident are you that you could catch a fly using a fly swatter? That you could catch a fly using a pair of chopsticks? That you could catch a fly using a pair of toothpicks, right? As your interval, as your tool gets smaller, your confidence goes down. So as your confidence level increases, the interval will get wider, and vice versa. As your confidence level decreases, your interval gets narrower. So the more confident you are, the wider your interval. The less confident you are, the smaller your interval. That can sometimes feel a little bit backwards or weird, but the confidence level is saying how sure you are that your true answer, that the true whatever, proportion, mean, whatever, is held within those two numbers. If we want to be more confident in our answer, we want to be more confident that our interval actually includes the answer, we have to widen the interval, and vice versa. So I could, for example, say, I'm 99.9999% sure that tomorrow's high temperature will be between 0 and 100 degrees. I'm very confident because my interval is very wide. But is that very informative? Not really. That doesn't really explain to me how I should, should I wear a jacket? Should I bring an umbrella? This doesn't help me with that information because it's very, very, very vague. So there has to kind of be, and this is where statisticians struggle sometimes, there has to be a balance between how confident we are in an answer in an interval and the width of the interval. And then also just know that sample size also plays a part in that as well. Sample size is part of the formula for our standard deviation, right? So our sample size is also going to play a role in how wide or narrow our interval is as well. All right, let's talk a little bit about that critical value. So that's the confidence level number that determines how wide or narrow our interval is going to be. It is a z-score because it is called z-star, but it's a specific z-score. So thinking about if I have a normal model, right, when I say that I'm whatever percent confident, what I'm doing is I'm saying that I want my normal model to include 90% of the values. So I'm trying to figure out what are the middle 90%. So if I said I'm 90% confident, then I'm trying to figure out what is the middle 90% of values around the mean. So I need to figure out what this z-score is that's kind of on the upper end of that middle 90%. You can kind of think of it as my mean's in the middle, and I need to know how many standard deviations up and down do I need to go to get this interval. So it is a z-score. To figure it out, I know I want 90% in the middle, right? That leaves 10% left over, and that's going to have to be split between my two little tail regions. So that means in each little tail region, is 5% or 0.05. So what we would do from there is I would go to my z-table and I would use the z-table backwards. I know that 0.05 is this lower area. And then I know if I think about the upper area, we want the upper area to be 0.05, which means the area below that upper z-score is 0.95. So I'm basically using my z-table backwards and I'm looking up the area, the proportion that I want, which remember is inside the table, and I'm looking up the z-score that corresponds with it. So for example, if I were to go look at a z-table, and if I were to look up the 0.05, which is the lower end, so I'm going to look inside the table where the proportions are, and I'm going to try to find 0.05 or as close as I can get to it, right? There's kind of two answers. There's two proportions in here that are equally close. There's 0.0505 and 0.0495. You could use either one. So once I find that number, I'm going to look up what z-score that is. So this is negative 1.64 or negative 1.65. Either one, or you can split the difference. So that is a negative z-score, which makes sense because that lower 5% would be on the left side. Basically, our z-star in that case would be 1.65. Remember, we're going to add and subtract our margin of error. So in terms of the plus versus minus, it doesn't really matter because you're kind of doing both. But you could also look up, if I wanted to look up the upper one, right? 0.05 is above, so 0.95 would be below. So if I looked up on my z-table 0.95, let me see if I can find the other part of it, right? 0.95 or as close as I can get to it. Again, there are going to be two that are similarly close. There's 0.9495, 9505. That z-score is 1.64 or 1.65, so it's positive. So it's the same z-score on either side. We are adding and subtracting it. So the z-star we would use for 90% confidence is 1.64 or 1.65. So similarly, if I wanted to find 95% confident, again, there's 95% in the middle. That's what that represents. If I wanted to find that z-star, that z-score, I know 95% is in the middle, which leaves 5% on the outsides. Split into two little tails gives me 0.025 or 2.5%. So I could go to my z-table and look up 0.025 would give me the negative version of that z-score. 0.975 would give me the positive version. It doesn't matter which you look up. We're just going to add and subtract it anyway. But 0.025 is right here, which is negative 1.96. So 1.96 is my z-star, which is what we used earlier to find that first confidence interval, right? And then 99% confident, I'll show you this way to use it on, if we wanted to do it on the calculator. Again, 99% is in the middle. That leaves 1% left for the two tails. Split in half is 0.5% or 0.005. And I can use my calculator. I can use my z-table just like I did a minute ago. But if I wanted to use the calculator, second vars, and then we use this one that says inverse norm, means normal backwards. And then I'm going to put the area as 0.025 or not 0.25, 0.005 was on the last one. If you have these options of left, center, right, just keep it on left for now. We can talk about that another day. And then it'll give me the z-score. So negative 2.5758, etc. So 2.576 would be that z-star. So that is how we kind of use or find what z-star to use based on how confident we want our interval to be. All right, we're going to put it all together and talk about assumptions and conditions and then do an example problem. So I'm going to actually put that in a separate video. So this was more a video of kind of the introduction of the idea of a confidence interval. We're going to talk about assumptions, conditions, and then talk about how to actually do a complete confidence interval problem in the next video.